It is delta S of mixing is equal to minus NR XA log of XA plus XB log of XB, and this is the case for ideal gases, constant pressure and temperature. It's a very special case, but just do that because I just like that experiment. Okay, we'll see some more cases of calculating entropy, and some of them are quite straightforward, right? So if I heat something, right, from temperature, let's say some substance A goes from temperature T1, volume is V, goes to temperature T2 at volume V. So heating or cooling, whatever it is, at constant volume. Heating or cooling at constant volume. And then I want to calculate the change in entropy of this system, right? That's fairly simple, straight from the definition. Delta S is equal to going from state 1 to state 2 dq reversible by T, which is equal to T1 to T2 Cv dt, because we are at, the process is at constant volume, Cv dt by T. And if the temperature difference is not so much, then Cv is temperature independent, it can be treated as a constant. What you get is Cv, just one moment, log T2 by T1. Yes, tell me. It's not working. I'll try to shout as much as I can. Okay. And yeah, if somebody has a hearing problem, then the front row, at least 4 of them here, and another 6 of them there, they are empty. Most welcome to join here. But yeah, if you're quiet, I'm sure you can hear at the back. Right. So this is one of the equations that kind of, it should be just maybe memorized. Cv log T2 by T1. Okay. So in this case, delta S would be positive if T2 is large, right? That means I'm pumping heat into the system. We could think about phase transitions. So reversible phase transitions, which are very important because that is what you'll be dealing with most of the time. Reversible phase transitions. And for all practical matters, these would be at constant pressure, right? And in most cases, the phase transitions, when they occur, the temperature is also constant. Right? So you could think of water going from liquid 0 degrees C 1 bar to water going to solid, or let's do it the other way around. Solid water at 0 degrees 1 bar going to liquid water at 0 degrees 1 bar, right? What is the heat that has been absorbed? the heat absorbed is at constant pressure, which is equal to just the delta H of fusion. Okay, so the delta S of fusion in this case would be equal to delta H of fusion divided by the constant temperature at which this process is occurring. Right? In general, I can just write that delta S of a transition is equal to delta H of the transition divided by the temperature of transition. Related to this, there is one question in Q2, which is already online. I'll put it in Scoops today. That reminds me, I have another important announcement. You have a quiz on Tuesday the 21st, which is a Monday timetable actually. So you have a class. The quiz is between 6:30 till 7. It's 10% of your total marks. And for this section, it will be held in workshop 204, 209 and 213. You can sit wherever you feel like. Syllabus, whatever we learned till today. Monday will be excluded. 204, 209 and 213. So they're all on the first floor of the workshop. You can sit in either room. Doesn't matter. Fine. So this question in the tube that you've been given is water and somehow I have been able to bring down this water to minus 10 degrees C. So water is a liquid at minus 10 degrees C, 1 bar. Okay. And then I somehow induce crystallization of this water. This is called supercooled water. Okay. And there are lots of examples of supercooled states, for example, glass. Okay. These are all supercooled states of matter. So we have a liquid at minus 10 degrees C, 1 bar. But then, of course, it is not a stable thing. It's not a stable situation to have water at minus 10. The moment you disturb it, it crystallizes into ice. So irreversibly, it doesn't come back to minus 10 liquid water, but what it does is it goes to solid water. For the moment, I'll hold it minus 10 degrees C. So this is irreversible. Now remember, if I want to calculate entropy, I always have to find a reversible path. And in most of the questions, you have to determine what the reversible path is. Right? So in this case, I have to first construct a reversible. It doesn't matter which path I take, the change in entropy is going to be the same. Right? So I might as well construct a reversible path and find my value of delta S. So how do I go about this one? Increase the temperature, right? So water which I have supercooled down to minus 10 can be again heated up and brought to 0 degrees Celsius reversibly. Water, liquid, 0 degrees C, 1 bar. This is reversible. A phase transformation happens at 0 degrees C for water at 1 bar. Right? So that's reversible. Water solid 0, 1 bar. and a solid can be cooled down to -10 reversibly. That's another reversible process, right? Huh. That's no, it's not hypothetical. You can achieve these states provided no, with 1 bar. Okay, supercooled states are possible. These are not represented on the phase diagram of water, the normal phase diagram that you see, but supercooled states are definitely possible. Okay. So if I want things to crystallize, this has to be a reversible process. So I have to do it very slowly. If on the other hand I cool it down very fast, okay, without disturbing the system too much, then it's possible that I can cool it down below 0 degrees as well. In fact, practical example is a glass. This glass which you see on the windows is a supercooled liquid. It's not a solid. There's a definition of the solid. Solid is crystalline. Or even if it's amorphous in nature, then also there are some shortage. This is more like a liquid state. Okay. Yeah. So then I have to worry about the heat exchanges that occur, and this one would be just Cp dt by T. Cp of the liquid, that would be Cp of the solid. Take care of the temperatures where you are starting from and where you are ending, and then you won't have any problem with the signs. That would be delta H of fusion by T. Okay, not 0, converted into the Kelvin scale. Don't get infinite values for the change in entropy. Okay. Now we need to move towards the third law, which is, I've shown you already in the case of the Carnot engine that you require infinite amount of work to achieve 0 Kelvin, right? So you cannot actually achieve 0 Kelvin, but you can go very close to it, right? In fact, temperatures of nanokelvin I know have been achieved in some experiments which deal with things called Bose-Einstein condensates. So you don't have to bother much about it for the moment, but you can go down to very low temperatures. But the thing is, if you want to reach 0 Kelvin, you need infinite amount of work. So you cannot. So that's one manifestation of the third law. But we'll just go through what exactly it means. Fine. And to go through that, we'll just look at some of these equations. Okay. So let's say we have the first law, which is du is equal to dq minus p external dv, right? And we have the second law, which says dq reversible is equal to t times ds, right? Now I do one thing, I put a reversible over here, right? Du does not change. So let's consider only reversible changes, Instead of P external, I'll have PdV. If that is the case, I can substitute dq reversible by TdS and get this expression du is equal to TdS minus PdV. What's so special about this equation? And work? That definite. All of them are state variables or state functions. Each one of them. U, S, T, P, V. All state. Does not depend on the change. Right? If these are all state variables, I initially assume that the change be reversible. But these are all state variables, so it does not matter whether the change is reversible or irreversible. This equation holds true for both reversible and irreversible cases. Why? Because it really does not matter how the volume changes. It only matters what is the initial and the final volume. Right? So this P is a state function. P is a state variable. Volume is a state variable. Right? And PdV is the reversible work done, so I've already defined a path. So I know it. But what I'm saying is all the variables are state variables, or all the functions are state functions, whatever you want to call them. So it really does not matter. Right? Does not matter on the path. So reversible, irreversible, this is always true.
But sir, it is irreversible, we can't come to the equation.
We can't derive this equation, that's true. But once we are here, it does not matter. Right? And definitely there are more rigorous ways of deriving. We can.
PdV, we have defined it reversible, okay, but reversible adiabatic or reversible isothermal, PdV term is going to change.
Yes.
So how can that be said?
But it doesn't matter. All I'm worried about is what is the pressure, what is the change in volume. That's it. Even if it's an irreversible process. Right? The change in pressure, the pressure would be different for an irreversible adiabatic change for that matter. Won't be the same. So I have a different value then. You know, it would lie somewhere between the pressure of isothermal and adiabatic. Okay. So this is a fundamental equation with just state variables. Okay. So it seems we started with defining the internal energy U as a function of temperature and volume. It was more intuitive, right? Because it changes, we can see the changes in volume and temperature. But mathematically, it seems that since all of these are state functions, entropy and volume seem to be a more natural choice. Okay? They're kind of units that are more internal to the internal energy, right? These are more naturally suited units. So, I could say that the internal energy U is a function of S and V. And I would say that these are kind of natural variables. And since the internal energy is a function of entropy and volume, I could write the total differential du as a change in entropy and a change in volume, right? So what I can write is that du is equal to du ds del u by del s at constant volume times ds plus del u by del v at constant entropy times dv. And what do I recognize this then as? This fellow is equal to minus pressure. This fellow is equal to temperature. Right? Similar things I can do with enthalpy. Right? Huh? So dH is equal to du plus d times PV, or I could straight away write PdV plus VdP, right? And then I could invoke the second law now, where I already have du is equal to TdS minus PdV. I have already got this information, so I put this in. So TdS minus PdV plus PdV plus VdP, and these two just cancel out, so I'm left with again all state variables. So a more natural choice for enthalpy then is a function of entropy and pressure. Right? And then I can easily identify del H by del S at constant pressure is equal to temperature, and del H by del P at constant entropy should be equal to volume. Everything clear? Great. And now from these two fundamental equations, I can also get some of these things. I wanted to know how exactly entropy varies as a function of temperature with, you've been using this formula Cp dt by T. How does it come about? The variation of entropy with temperature at constant volume. So you already have the equation du is equal to TdS minus PdV, right? And from here I just divide this by dt at constant volume. So what I get is del u by del t at constant volume is equal to T times del S by del T at constant volume. Right? Temperature is not constant, it's changing, huh? So what it just gives me is that del S del T at constant volume is equal to 1 by T Cv Likewise, I should be able to get del S by del T at constant pressure is equal to 1 by T Cp if I use the formula for dH. Clear? So, just want to show you some of these equations. And I mean, the Euler's criterion takes partial derivatives to prove that something is a function, but I didn't get your question right. There's a confusion, that's why I want to get that. Yes. Yes, no, that's why there's some confusion on this. Because no thing. This is very important. Partial derivatives and state functions are two different ideas. If I could understand the nature. Okay. Anyway, so now what we go ahead and look at is to define entropies. How do I calculate the entropy? Now, if I heat up something and I stay at constant pressure, then I already have a formula over there. Del S by del T at constant pressure is equal to Cp by T. So delta S would be equal to Cp by T times dt integrated from the initial temperature to the final temperature, right? So what I could look at is that, let's say I have some substance A and I want to see what is the change in entropy of this substance A if I start from 0 Kelvin and heat it up all the way to, let's make it a gas. Okay. So I'll be going through these changes, right? A, let's say it's a solid at 0 Kelvin, and then reversibly I heat it to solid at its melting temperature. Everywhere we are, let's say, at 1 bar. Constant pressure. Okay, and then I take it from there. It melts, becomes a liquid, still at the melting temperature. I heat it. It's all reversible, right? Goes to the gas at goes to a liquid at the boiling temperature, goes to gas at the boiling temperature, right? And then I heat it further so that it stays into a gas at some temperature T. I wish to calculate the change in entropy. Or so the change in entropy would be, if I can define it, the entropy at temperature T, right, minus the entropy at 0 Kelvin. okay, which would be equal to, first step was heating, so it would be equal to integral from 0 till the melting temperature Cp of the solid, and now I'm not assuming that the Cp is constant, it can change, okay. Right, plus then it's from solid to liquid, so delta H fusion by the temperature of melting plus from the melting temperature all the way to the boiling temperature Cp liquid dt by T plus then we have delta H vaporization by temperature boiling so we are here somewhere, and from the boiling temperature to our final temperature Cp of the gas, right. I just do one thing over here, instead of this minus I write an equal to and put a plus over there. If I can do that, if I can define this quantity. Can I define this quantity is the question. And if I can define this quantity, yes, I can. Right? So the third law relates to exactly this question. In fact, in let me just read some statements, or rather tell you. In fact, in 1905, this was known as the Nernst heat theorem, okay, which said that as T approaches 0 Kelvin, delta S approaches 0. Not S, but delta S approaches 0 for all isothermal processes in condensed phases. So it's reasonable enough to assume that at such low temperatures these are condensed. Okay. How is it isothermal? Okay. How is it? Okay, that's a good question. How is it isothermal? All these processes. Any idea? What you can measure is the entropy change without a change in temperature. Right? And the thing is that when the temperature does not change, still delta S approaches 0. That is the main idea, right? So when my temperature is very low for any isothermal process at that point, the entropy change tends to be 0. That's all it's saying. There you go. Then in 1911 came Max Planck and he said that as temperature approaches 0 Kelvin, it's not just delta S, but the true value of entropy S approaches 0 for, now this is very important because a lot of students and everybody makes errors if they do not go by the definition word to word. For every chemically homogeneous substance in a perfect crystalline state. Okay, that's very important. Now the thing is, again, it's a law. The third law is a law. So you don't expect to prove it, but it works. And it works beautifully. And a few days back I had shown you this, that the entropy, the value of entropy is equal to K natural log W from the Boltzmann analysis, right? And W, for a perfectly crystalline substance, if you arrange anything, you have only one possible arrangement, one microstate. So from statistical thermodynamics also, it gives you a value of 0 to entropy. Okay. So the thing is that we can calculate the values of entropy if we actually know the number of defects. Then we know the number of microstates. Okay. For example, monoatomic molecules have only one orientation. They don't have many possible orientations. But you can think of diatomic molecules. Right? They could have various numbers of orientations. They could be head to head or head to toe aligned. Yeah. If I have, for example, carbon monoxide, or so I could have carbon oxygen and then carbon oxygen, or it could be carbon oxygen oxygen carbon. There are two different ways of arrangement. If I have and the thing is that the difference in energy is not so much, so they can convert from one form to the other. That's very important. If the difference in energy is high, then of course they cannot interconvert, so they are stuck in one microstate. In that case, the entropy would be 0. If the difference in energy is high, because right, only then you have to worry. If the difference in energy is low, then you can count all these microstates. Another way could be diatomic, homonuclear diatomic molecules, which could be arranged like this or could be arranged parallel to each other. That could make a difference. Right. So all these things can be evaluated, at least in principle. Maybe in a number of cases you may not be able to count, but in principle, yes, these can be evaluated. Okay. Now, we've already seen that you need infinite amount of work to reach 0 Kelvin, right? So there's a corollary of the third law, which says that it is impossible to decrease the temperature of any system to T is equal to 0 Kelvin in a finite number of steps. So you see, temperatures, very low temperatures have been achieved, but you cannot go to absolute 0. So this equation, maybe I could just tell you, because tells you another another situation where you can calculate the change in entropy also. Infinite number of steps you can achieve it. So let's think of 1 mole of ideal gas. Okay. So du is equal to Cv times dt, right? And if this is a reversible change, then I can write Cv dt is equal to T ds, right, which is dq reversible minus P dV, or since P is equal to RT by V, let's write RT by V dV, right? And from here I can get a general expression for ds, is equal to CV d log T plus R d log V, and if I integrate it, get the value of delta S is equal to CV log T2 by T1. You've already seen this, plus R log V2 by V1. If I want any spontaneous process that should take my temperature, T1 is the lower temperature, right? So if I want to take the temperature to a lower temperature T1, then this delta S should be greater than 0, right? But let's say that I have achieved 0 Kelvin and I want to take down the temperature further. That means T2 is 0. This fellow is minus infinity. Yes? This fellow means plus infinity, which is not possible. Right? That much amount of entropy I have to supply. I have to increase so much entropy infinite times that such a process is not possible. Another corollary to the third law is that even if you manage to come to 0 Kelvin, you cannot stay there. Okay. You cannot stay there because, you see, what is the change in delta S? The change in delta S is, delta S is Cp. So from 0 Kelvin to whatever temperature I want to take it. Let's say a very small temperature, not too large. So it's a Cp of the solid divided by T dt. Now, if I am at 0 Kelvin, then the heat capacity has to be 0. Right? Otherwise, this term would blow to infinity. Which means, if the heat capacity is 0, any stray amount of heat that comes out from the surroundings would raise the temperature. Right? It can only happen that we stay at 0 Kelvin if we have managed to achieve it somehow, only in case of a totally isolated system, which is impossible to find. Right? I have some traps for me. Just a word of caution, I already told you, this has to be chemically pure, homogeneous system, crystalline system. Okay, make sure of that. If two gases mix together, there is always an entropy. If two solids mix together, we can use the same equations, minus NR XA, right? It's for an ideal solid, let's say. We would, in fact, we get an equation of that sort. If they mix together, we would have an entropy. But remember, this is not a chemically homogeneous mixture. It's not a pure crystalline substance. Okay. So in those cases, yes, you will have some residual entropy, There are lots of cases where you have residual entropy, and each of the case you can easily figure out why it has. We could take up some specific cases also later. Right. So we have any questions till now? Yes?
So explanation of this feature.
Uh-huh.
Explanation of this feature.
So it just says that if you are approaching 0 Kelvin, the change in entropy would be, so again there is no explanation, but
No, that the box isothermal and get T tends to 0.
no, all it says is that for any isothermal process, he's able to calculate delta S for isothermal processes. Right? So if I am at a very, very low temperature and I wish to calculate the delta S, it is easy to calculate for an isothermal process, right? You just equate it to the work done. So if I am at low temperatures, what he must have observed was that he kept on decreasing the temperature and kept working with these things, and he saw that the change in delta S becomes less and less. Okay. That's what my understanding would be. This one. So if temperature is 0, this fellow has to be 0. If not, this term would blow up. Okay. You would have an infinite change in the entropy. CP has, okay, good. CP has actually, experimentally, CP has a temperature dependence, which is of the form CP is equal to gamma T plus something, okay, gamma 1 T plus gamma 2 T cube plus so on and so forth. So if I go down to temperatures of 0 Kelvin, CP does go to 0. Huh?
CP by T would not.
CP would go to 0.
CP by T would not go to 0. It will be gamma 1.
Right. So that's what we don't want it to go to 0. Right? Of course, first thing is T is equal to 0 is not approachable. The other thing is, if we are at T is equal to 0, then this fellow also is 0. You don't want this term to blow to infinity.
So here you have written delta S is greater than equal to 0.
For a spontaneous change.
So delta S greater than equal to 0 is for isolated system or the whole universe.
Yes.
And here we have taken only system, not
So-
surroundings into consideration.
Yeah, so actually what I missed out was that this system, let's say this is adiabatic. Okay. Yeah, I think I was being too fast, so I missed out that part. Only then you can have that speed.
I mean, we haven't even reached to 0 degree Kelvin, and we say that there is a temperature of 0 degree Kelvin. So
This is?
there is no temperature below 0 degree Kelvin.
Yes.
We say, but we haven't reached to 0 degree Kelvin. So how do we know that there is no temperature below 0 degree Kelvin? It cannot be 0 degree, so we cannot reach.
No. This is, I think, the first lecture where I showed you the Boyle's law.
Yeah.
You cannot have negative pressures, you can't have negative volumes. Remember?
Yes.
Limit of PV approaching 0. Yes. It is the ideal gas scale.
Yeah.
Just, okay, good that we have it from the record, so you can access it anytime and see.
Making it adiabatic, how do we ensure that the inverse is greater than
So now it's, there's no heat exchange with the surroundings, right? In fact, last time you even asked me this thing. The Q is dependent on temperature and the delta S is dependent on temperature and volume.
So there is no mechanical contact also with surroundings.
Doesn't matter. Nothing is allowed to leave or enter. It's a closed system. It's a device.
But if some mechanical contact is there, then it will not remain isolated. Even if some matter is not leaving, it's
No,
a closed system, then also we can have mechanical contact and works can be done. So then it doesn't remain an isolated system.
Right. See, isolated system just means that no heat is allowed. Adiabatic system just means that no heat is allowed to escape the system or enter the system. Right? A thermos flask is an example of adiabatic system.
Adiabatic system doesn't necessarily mean that it is an isolated system.
What does it mean? What else does it mean?
Isolated system, work also need to be zero in isolated system.
So we can do work. In adiabatic system, we can do work. Right?
That means adiabatic system are not isolated.
Yes.
So then why are we using the delta as well? In the adiabatic condition we have put it down. And then we are using delta as greater than equal to 0.
So what do we have over here? Yeah? Let's go back. Big deal. I mean, just make it isolated. Okay. Yeah. Since work can be done on your surroundings, right? It should not. There's no heat exchange with the surroundings, right? Yes. Yeah. So there's no heat exchange with the surroundings. So whatever the delta S is of the system, that should be greater than 0. Right?
I agree that the delta S will remain the same, but using the condition that delta S is greater than equal to 0 will not be right if the system is not isolated.
No, even in case of adiabatic, the thing is that there is no heat exchange with the surroundings. So there is no change of entropy of the surroundings. Right?
So according to that, heat can enter into the adiabatic system, but the temperature will decrease. It says energy transfer into the not the
No. Some mistake over there, please. Read it again. Right? Is that fine? I mean,
Sir, in an adiabatic system, the matter may exchange, but in isolated system, matter cannot exchange.
so we are limited to closed systems only. We are not allowing matter to get exchanged, right? Are you happy with adiabatic? I mean, there's no exchange of heat. The surrounding does not get any heat, right? Or lose any heat. So that means there's no change in the entropy of the surroundings. Remember, okay, maybe I get back to this one. The surroundings has an infinite volume. Always assume that.
Infinite reservoir.
Right. No, volume. So you never consider a change in volume of the surroundings. Yes? Maybe that was confusing. So the only way a surrounding can increase or decrease its entropy is by exchange of heat. Okay. And now you've been waiting for how to get those two identities which I have told you, right? We'll work towards it. Fine. I'll introduce the concepts of free energy today. There are two free energies which we know of, Helmholtz and Gibbs free energies, and we'll do that now. What we'll do is we'll establish the criteria for spontaneous changes. Okay, because that's what we actually want to see. We know the general criteria for spontaneous changes is that the entropy of the universe must increase. That's a spontaneous change. Okay. But when you are doing some other stuff, then every time you cannot fall back and calculate entropy. There are other things which you can calculate. For example, when you're doing your chemical reactions at constant pressure, then the most useful quantity that you know is delta G. And we already, some of you already know that delta G should decrease for a spontaneous reaction. We'll come to those criteria in a short while. But let's start from the very basics. The second law, the Clausius inequality, ds minus dq by t is greater than 0. ds is greater than or equal to dq by t. That's the second law. That's the starting point for spontaneous processes. Okay. Let's consider one example where, okay, I don't have the mic, so if you be a bit more silent, then everybody could hear me, perhaps. So the first one, heating at constant volume. And for the moment, let's consider only expansion work. Only expansion work. Okay. Now, the heat exchanged is dq at constant volume. The work done is 0. Since we have only expansion work, and dV is 0, so this is simply equal to du. And I could then write the above, the Clausius inequality. I could write this as ds minus du by t is greater than or equal to 0, or TdS is greater than or equal to du. Now I am already holding one of the criteria, volume as constant. One of the variables, volume as constant. Now du was equal to TdS plus PdV minus PdV. I am holding volume constant. If I hold u constant, temperature is always a positive number. So ds at constant volume, constant internal energy is always greater than equal to 0. Likewise, du at constant volume, constant entropy is less than equal to 0. Yes? Yes, I get it from the other equation, from the second law. Yes? Huh? Yes? The? So, I am Worried about, okay, I could have said no additional work. Only PV work, that's it. No additional work that I am considering. No electrical work, no surface tension, nothing else. Why? Sorry? Huh? I didn't mention any ideal gas at all. No, no, no. See, this is, if I write like this, du is equal to dq plus dw is equal to dq minus p external dv. This is true for everything. And now I just put a constant volume criterion. So this just goes out. Okay. These are very general, not just for gases.
So we have PDS is du plus PdV. So we have PDS is du plus PdV. So if u and v are constant, so ds will be 0.
That's for reversible.
So by taking this equation is for both reversible and irreversible.
Yes.
So if v and u are both constant, then du and dv are both 0.
That's not for a spontaneous case. That's not for a spontaneous case. In case of a when things are spontaneous, then it's this is the one that you have to use, right? See, there we started with ds minus dq reversible by t is equal to 0. That was for a spontaneous case. Oh, sorry, for a reversible case.
You can see the equation is written true for both reversible and irreversible. So irreversible is spontaneous. Spontaneous, right? So using this equation, we get a constant u and v ds is 0.
Right.
So but it is
Now, remember one thing. I talk of a spontaneous. Very good example is the adiabatic expansion. The reversible case takes you to a different point when it's spontaneous. Isothermal expansion, you can come to exactly the same point. Reversible and irreversible. Now you see what happens. Okay. Fine. These are two practical cases. So heating at constant volume, and the other would be heating at constant pressure. Yes. But I also showed you this one, right? Did I show you this one? No. Okay, then we could do that. Well, I think I did. ds minus dq by t is greater than 0. Yes. I think I did. Yes. So that's it. In general, it's greater than or equal. If it's reversible, it's equal. If it's irreversible, it's greater. I thought I'd done this. Okay. So the second case would be heating at constant pressure only expansion work again. Okay. In this case, you can calculate dQp is equal to dH. And if I substitute dH over there instead of dQp, what I'll get is TdS greater than or equal to dH. So the criterion for spontaneity in case when you're holding the pressure constant is either that the entropy change at constant pressure, constant enthalpy is greater than or equal to 0, or the enthalpy change at constant pressure, constant entropy is less than or equal to 0. It's quite analogous to this one. See, the thing is, what's very important over here is to realize that it's not that I'm holding the entropy constant. The second law says the entropy must increase, and so it does. The internal energy of the system decreases. How would it decrease? By throwing out some heat. This heat goes to the surroundings. The entropy of the surroundings then increase. Okay. In totality, the entropy of the universe does increase because that's where we started from. Yes, this entropy is only entropy of the system. Remember, when we said ds minus dq by t is greater than 0, then ds is the change in entropy of the system. Is dq reversible by t, right?
So in that equation, ds is for the whole universe.
Huh? Actually, to be very frank, ds is of the system and dq by t would be that of the surrounding. And that's what we do, right? Delta H system plus delta H surrounding is greater than 0. Or minus dq by t. Because that is the heat that has been taken from the system to the surrounding. Q is the heat taken from the system to the surrounding. So minus Q is the heat that goes to the surrounding. Okay. So now what you're seeing over here is essentially du minus dds is less than or equal to 0. Right? Or in the second case, dH minus TdS is less than or equal. So let me write it that way. du minus TdS is less than or equal to 0, or dH minus TdS is less than or equal to 0. So this, why don't we define something then, right? Let's define this as, the left side, let's define this as A is equal to U minus TS, and here let's define G is equal to H minus TS. Two functions. This fellow A is called the Helmholtz free energy, and this fellow is Gibbs free energy. Poor Helmholtz did not have a choice to keep H his own name, huh? So, why he chose A of all this? He is a German guy. A stands for Arbeit, that's work. Okay, and we'll see in the next lecture that don't close it now. You'll see in the next lecture that actually delta A is the maximum amount of work that you can extract from a system. I give you free attendance today, off the record. Okay. Okay, just one moment. Before we wind it up, hang on. At constant temperature, right? If I actually were to write dA is equal to du minus T ds minus S dt, right? Please. At constant temperature, dA is equal to du minus TdS. And we've seen the criterion for spontaneity over here is that this fellow should be less than equal to 0. Similarly, dg would be dH minus TdS minus S dt, and again at constant temperature dg would be dH minus TdS, which should be less than or equal to 0. So what it gives us is dA already we had one precondition over here, the volume was constant, and now the temperature is also constant. For such a process, dA should decrease, the free energy of the system should decrease. These are more useful equations when it comes to designing reactors or doing reactions in the lab at constant volume or constant pressure. Now there are lots of reactors which are closed, more like the pressure cooker. That's a constant volume process. U minus Cs. That's it. Right. Helmholtz free energy is the maximum amount of expansion work that can be obtained. Huh? This is the maximum amount of work that can be obtained by this. Maximum. Delta G is the maximum amount of additional work that can be. It's not that the system will obtain that much. I'll come to those things in the next lecture. Yes. Pressure? Yes. Right. 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 There is a possibility of delta G equals 0. You come to the physics.